In this video, we will discuss Ohm's law, electromotive force or the EMF, and we will see how these two concepts are associated with electric circuits. First, we will discuss the details of Ohm's law. Along the way, we will introduce a few important circuit symbols for components such as resistors and batteries. We will then introduce the concept of EMF and terminal voltage and solve a few problems based on these concepts. Let's first look at Ohm's law. Assume you have a resistor like that. This is a circuit symbol for resistor with resistance, let's say R ohm. This resistor is connected to a battery, so that is the circuit symbol for a battery, like that. The longer line, as we have discussed before, corresponds to the positive terminal of the battery, and the shorter line is the negative terminal of the battery. Now let's assume the voltage that this battery can provide to the rest of the circuit is V volts. Now since this circuit is complete, you will have flow of charge and therefore current going in a following manner. Let's assume the current is I. The unit for current is of course ampere. One thing to note is the direction of current is always from the positive terminal all the way to the negative terminal, as indicated by the arrow. We are going to assume that R, the resistance of this resistor, is a constant for variety values of V and I. Ohm's law states the value of this current in the circuit is dependent on the voltage provided by the battery. And not just that, this dependence is proportional. Or we can say the current is linearly proportional to the voltage provided by the battery. The constant of proportionality turns out to be the resistance of that resistor, namely capital R. This means if we were to replace with a stronger battery, which will provide a voltage of 2V, the current in the circuit will be now 2 times the original current. So that is the simple proportionality, and that is the essence of Ohm's law. Graphically, we can represent Ohm's law in a following manner. Suppose we have a graph. V is the voltage, and the horizontal axis is the current I, with a unit of ampere. So V is measured in the unit of volts. The dependence of I on V can be sketched in the following manner. It is quite simply a straight line, and the slope of this straight line is quite simply the constant resistance of that resistor, capital R. So R here is the slope of this VI graph. Now we can see the SI unit for resistance, as we have already mentioned in our previous video, is ohm. And it's clear from the graph that 1 ohm is equivalent to 1 volt per ampere. So ohm and volt per ampere can be taken to be the SI units for resistance. Metals or conductors whose resistance exhibit such a behavior are known as ohmic materials. As we have mentioned earlier, this is the symbol that we use in circuits for resistors, and this is the symbol for battery. Let's look at the symbol for battery. Up to this point, we have labeled capital V to represent the voltage that is being provided by the battery. A more accurate representation of that value of the voltage that a battery can provide is the so-called EMF. That curly capital E is the symbol that we use for EMF. Now what is this EMF? EMF stands for electromotive force, but it must be remembered that EMF is not a kind of force. It is a kind of voltage. So the unit that we use to quantify EMF is volt. So from now, we shall represent battery with a symbol such as that. And this value, whatever the value is, represents the electromotive force of that particular battery. So typically, a complete circuit with a battery and a resistor look like this. So if you see a battery represented with such a symbol, it is readily understood that this voltage source or battery comes without an internal resistance. However, in practice, voltage sources will have a very small internal resistance inside of them. And we should be able to take this into account, and we will see that in a minute. For such a perfect battery or voltage source, the voltage provided by this battery to this resistor between the two ends of this resistor, let's call those two ends points A and B, equals to the EMF of the battery itself. And from Ohm's law, we know that is simply the current through the resistor times the resistance of the resistor. So whatever voltage the battery provides will get to that resistor. Now, what about battery with internal resistance? In this case, the symbol for that battery is as follows. So you have the same two lines, and you have an additional resistor with resistance little r, and since this little r belongs to that battery, we shall enclose them in a box like that. So this is how we represent battery with internal resistance. Now, if we were to connect this battery to, let's say, an external resistor with resistance R and complete the circuit would look like this. So let's say the EMF of the battery is E. The current from the battery will go in the same direction from positive terminal to the negative terminal outside in the external circuit, like that. Now the question is, what is the voltage provided by this battery to the external resistor between the ends of this resistor, namely between the points A and B? So that voltage, VAB, is no longer the same as the EMF that is provided by the battery, because now you have a certain compensation due to that internal resistance of the battery. To understand this, let's for the moment take this little r and assume that it exists separately from battery with EMF E. So in that case, we can write the EMF as providing voltage to two resistors, the first resistor and the second resistor. So the voltage across the first resistor is quite simply I times little r, and the voltage across the second resistor is I times capital R. I times capital R is indeed VAB, which is that one, namely the voltage across the resistor capital R between points A and B. By slightly rearranging that equation, we see that VAB is quite simply the EMF minus IR. Now we can clearly see the fact that VAB is not the same as the EMF. Another thing is that we can also see the VAB is indeed less than the EMF. So VAB is also known as the terminal voltage. So the point is not the entire EMF from the battery will get to this external circuit due to the presence of internal resistance inside the battery itself. Let's look at this simple exercise. So you have a battery with EMF 12 volts, internal resistance 2 ohms, and external resistor 4 ohms. You want to determine the current in the circuit and also the terminal voltage VAB, namely the voltage across that external resistor. By using the equation that we have just introduced, EMF being I internal resistance plus the external resistance, we can determine I as quite simply the EMF over the sum of the two resistances. And that's going to be 12 over 2 plus 4. So that is 2 ampere. Having found I, you can determine the terminal voltage, which is the voltage across this 4 ohm resistor, as quite simply I times 4. Since I is 2 and 4, you get 8 volts. You see clearly that the terminal voltage is less than the EMF, namely 8 volts, and the EMF is 12 volts, due to the presence of the internal resistance. Let's look at the following problem. A battery has an EMF of 15 volts. The terminal voltage of the battery is 11.6 volts, namely the voltage across this resistor here, VAB, is 11.6 volts. While it is delivering power to an external resistor capital R. The current through that capital R resistor is 1.5 ampere. What is the value of capital R and what is the internal resistance of the battery, namely the value of the little r? Note, EMF equals I little r plus the terminal voltage. So EMF is 15, terminal voltage is 11.6, and that equals IR, I being 1.5 times little r. And we can solve for that internal resistance, which is 2.27 ohms. So this is part B. Part A, the value of capital R. We know the terminal voltage is current times capital R. Terminal voltage is 11.6. I is 1.5 times capital R. And therefore capital R is 7.73 ohms. That solves the problem. Problem 2. A battery having an EMF of 10 volts delivers 120 milliampere when connected to a 75 ohm resistor. Find the internal resistance of the battery. So using the usual equation, I little r plus the capital R, EMF is 10, the current is 120 milliampere, converting that to ampere is 0.12 ampere, R plus capital R is 75 ohms. That's this one. Solving for little r, which is the internal resistance of the battery, we get 8.33 ohms for it. That solves the problem. Problem 3. A light bulb has a resistance of 240 ohms when operating at a voltage of 120 volts. What is the current in the bulb? So this is just a direct application of Ohm's law. V equals to IR. Now we know the operating voltage is 120 volts. Current we want to find. The resistance is 240 ohms. So solving for I, we get 120 over 240, which is 0.5 ampere. And that solves the problem. Thank you for watching.